opposite direction. Okay. Now, what is a rectifier? Now, rectifier which converts a sinusoidal signal, that is nothing but your AC signal. A rectifier converts a AC signal to unidirectional flow. That is not pure DC. Now, it will convert AC signal to the pulsating DC signal. We are calling that as impure DC signal. Now, at the end of, now this is a rectifier I am taking. For example, this is a rectifier block. In the rectifier, what it is doing? Input is your AC signal. Output you are getting the pulsating DC signal. Now, by connecting a capacitor or the inductor, by connecting a filter at the output side, now you can filter all the ripples present in the signal and the pure DC you will get. That means to convert AC to DC, there is a two-step process. First one is the rectifier, which converting AC signal to the pulsating DC, and the pulsating DC is converted to pure DC with the help of your filter. Okay, our topic we are having two things are there. The first one is rectifiers with filter, without filter. These two topics we are going to see today. Right, now filter, what the rectifier will do? Rectifier will convert sinusoidal signal to the unidirectional flow, that is not pure DC. And this filter, this part I am calling as filter will convert the unidirectional flow, that means impure DC to the pure DC. The output of the filter is nothing but pure DC signal. Now, rectifier plus filter both will convert the AC signal to the DC signal. If you want to convert any AC signal to the DC signal, you need a rectifier as well as a filter. Now, if you are not having the filter, the output of the rectifier is, it is not a pure DC signal. Now, see, for example, now this is a pure DC signal, horizontal line. Now, what is impure DC signal? The output of at this point is, now it is going to look like this. Now it is not a pure DC signal. Some AC ripples will present in the signal. Now to remove these AC ripples, now we are using the filters. The output of filter is a pure DC signal. This is going to look like this. That we will discuss in the next slides. Now, if the input to the rectifier is a pure sinusoidal signal, the average value of such waveform is 0. I think, what is a pure sinusoidal signal? Now, sine wave, which is having, this is a sinusoidal signal. What is the average value of this sine wave? Absolutely 0, because positive half of the cycle, it is the positive, half of is negative, both will be cancelled, and the average value is nothing but your 0. This is a simple thing. Now, what are the different types of rectifiers we are having? There are 3 types of rectifiers are there. First one is half wave rectifier, second one is full wave rectifier, and the third one is a bridge rectifier. Actually, bridge rectifier is also comes under one form of full wave rectifier. Now, generally, we will call only 2 types of rectifiers, half wave rectifier and the full wave rectifier. Okay, what is a half wave rectifier? The name itself, it is saying half wave rectifier. It will rectify half of the wave only. This is my signal. Input signal is a AC signal. It will rectify only half of the signal. Now this is a half part, and this half part, and half part. Now only half of the signal, the rectifier which rectifies only half of the signal, that is a half wave rectifier. A rectifier which rectifies the full signal, that is a full wave rectifier. It is a simple difference. Now in half wave rectification, either the positive or the negative half of the AC wave is passed. Now it may be the positive half of the AC wave or negative half of the AC wave. Any one of the signal is going to be passed through the rectifier. Now while the other is going to be blocked. We will see the circuit diagram. Now with the help of circuit diagram, you will get the clarity. That means half wave rectifier will allow only the positive part of the signal. It will block the negative part of the signal. And again allow the positive part, it will block the negative part of the signal. Now that's why it is allowing only half of the signal. That's why we are calling this is half wave rectifier. Because only one half of the input waveform reaches to the output, it is very inefficient if used for power transfer. Now if you are using a half wave rectifier for power transfer, 100% power is not transferring, because the 50% of the signal is we are losing. Now that's why only the 50% of the power we are losing. it is very inefficient if you are using in the power transfer applications. This is about your half-wave rectifier. Now we'll see the circuit diagram for this half-wave rectifier. Now what is a half-wave rectifier? And till now we discussed the process of removing one half of the input signal to establish a DC level is called a half-wave rectifier. That means it will allow only one half of the signal. In a half-wave rectification, the rectifier conducts, that means the current during positive half cycle of the input AC signal only. The negative half cycle is suppressed. Now see here, see the diagram. Now it is a transformer, and now it is a transformer means now it is producing a sine wave. Output of the transformer is a AC signal. If it is AC signal, now this AC signal is applied to the diode. Now see, this is a diode. Diode, this is a positive and this is a negative terminal. Okay. Now the diode is connected at the one end of this transformer, and through the diode is a load resistance. We are collecting output at the load resistance, and this is a circuit for half-wave rectifier circuit. For this half-wave rectifier circuit, we have only one diode. In the full wave rectifier, we are going to see one more. See, this is not the diode. This is arrow direction. This is a current direction. This is arrow mark. Now this is our diode. Single diode is present in half-wave rectifier. Now what is going to happen? Now see, when the diode will conduct in the forward bias, diode will conduct. In the reverse bias, diode will not conduct. Now during the positive half of the cycle, see, this is the input signal. Now this input signal is applying at this point. Between this terminal and this terminal, you are applying as input signal. And now during the positive half cycle, now what is going to happen? Whenever it is raising, now when the diode will conduct, whenever it is greater than barrier potential, that is a 0.7 volts, then the diode will conduct. Now up to 0.7 volts, the diode will not conduct. Now, whenever it reaches to the more than 0.7 volts, the diode conducts, and the current will start flowing to the diode, and the output is going to be, it is going to appear across your load resistance. So that's why during the positive half of your cycle input wave, the diode will be in the forward bias. In the forward bias, diode will conduct the current that is going to appear across the output. That's why positive half of the cycle output is following the input. Now output, you can see the output during the positive half cycle. Now what is the negative half cycle? When the input signal is coming to this negative side, now if you are applying the negative, that means this is the negative and this is a positive polarity. Now this diode will be in a reverse bias condition. In the reverse bias, diode will not conduct. Now that's why during the reverse bias case, the diode is not going to conduct, the current is equal to 0. And once again, signal is coming to the positive peak, once again the positive side. Once again, this is polarity becoming positive and this becoming negative, and it is in forward bias. In the forward bias, diode will conduct the current, and once again the output, you can obtain the output. Now, whenever the input signal comes to the negative half, it is in the reverse bias, diode will be in reverse bias, there is no current flowing through the negative half of the cycle. Now that's why in the half-wave rectifier, it will pass only half of the signal, the remaining half is going to be blocked. That's why now it is rectifying only half of the input signal. That's why it is called as half-wave rectifier, HWR. That is a half-wave rectifier. I hope it is clear. Now what is a half-wave rectifier means? The rectifier circuit which will allow only one part of the signal, that may be positive side or negative side. It will allow only one part of the signal which will block the other part of the signal, you are calling as half-wave rectifier. The output of half-wave rectifier is looking like this. This is the current and this is your voltage. Okay, current, this I is current flowing through the diode, this is I, and voltage is what is your developing across the load resistance. This is a voltage signal, which will conduct only during the positive cycle. During the negative cycle, it is going to be suppressor. That is a 0. I hope it is clear to everyone. Now, the same thing what I said just now. AC signal across secondary terminals. This is the secondary terminals of your transformer. It will changes its polarity for each half cycle. During the first half cycle, it is becoming your positive and it is becoming your negative. During the second half, that means during this negative half cycle, it is becoming your negative polarity and it is becoming positive polarity. And during the positive cycle, once again positive and negative. Now the polarities are going to be changed for every half cycle. According to the polarities, the diode is also half of the cycle it is in forward bias, half of the cycle it is going to be in reverse bias. During the forward bias, it will conduct. At that time, you will obtain the output. During the reverse bias case, you will not obtain any output. The current is equal to 0 or output voltage is equal to 0. Now this is a half wave rectifier. Now this is a circuit diagram. See here, a simple. Now I will show you slowly. You will see the animation part. It is AC signal, smaller AC you are applying. Now see the output here, how you are getting. Now when it is coming down, it is positive half is coming, it is going to the negative cycle. Now there is no current flowing to the diode. See, there is no current direction in the diode. Once again it is coming to the positive cycle, there is a current flow through the diode circuit. And the positive peak will come here. And during the negative half of the cycle, there is no current flowing through the diode, that is in reverse bias, that is going to be achieved. Now this is a simple animation of your half wave rectifier. I hope it is very clear to you people. Now we will start the mathematical representation part. Now this is a half wave rectifier. It will rectify only half of the signal. These two are the images I have shown to you. Now output DC voltage equation calculations. Now output DC voltage of half wave rectifier can be calculated with the following two ideal equations. What are those? RMS value, average, as well as the DC value. Now these two are very, very important formulae. Now if it is possible, try take pen and paper just parallelly. Now whenever I am showing here the derivative part, you people also try to solve step by step. Then it will be very easy for you. Okay, these two are very, very important formula for us to derive the parameters of the half wave rectifier as well as full wave rectifier. What are those two? RMS voltage. RMS voltage is given by peak voltage by 2, and the DC voltage is given by peak voltage by pi. Remember these two formulae. Now these two formulae we are going to use nearly the 10 to 20 times in the today's class. Okay, remember RMS voltage, peak voltage by 2, DC voltage, peak voltage by pi. Okay, these are the two basic expressions we are going to use for today's part. Now what is the disadvantage of half wave rectifier? Main drawback is half of the signal only it is passing, it is rectified. Remaining half is it is 0 only. Now the pulsating current in the output contains only AC components whose frequency is equal to supply frequency, so filtering is needed. Now absolutely for the rectifiers, output is not pure DC, it is in pulsating DC. Now that's why output of rectifier, if you want to get the pure form of your DC, always you need a filter circuit. If you are not using the filter circuit, the output is not a pure DC form. Now this is one drawback of half wave rectifier. What is the drawback? The pulsating current in the output, which contains the AC components, AC ripples, whose frequency is equal to the supply frequency. So filtering is needed. Filtering is compulsory to obtain the pure DC signal. What is second drawback? The AC supply delivers power during half cycle only. During half cycle only, the AC supply is delivering the power. Remaining half cycle, it is not delivering the power. That means 100% power is not delivering. Only half of the power it is delivering. We are losing the half of the power. Now that's it. These are the true drawbacks of half wave rectifier. Okay. Now we will see the mathematical part of the half wave rectifier. Meanwhile, I hope this is clear to everyone up to this part. Just if it is clear, then text me in the text box. Is any doubts regarding to this? What is filtering? Yeah, exactly. Now filtering is nothing but, okay, I will show you with the help of some diagram. Now rectifier is, where do we use it? That is what I am telling. Now, if you take a best example of a normal DC supplies, if you are charging a mobile phones or these battery chargers are there. Now output of that adapter is nothing but you are getting only 5 volts or 12 volts output, pure DC you are getting. Okay. If these are our electronic devices, they are not tolerable with respect to AC signal. Now see, whatever the electronic device you are having, they are going to apply the DC signal. That may be the 12 volts, or that may be operating with the 5 volts. Now, if you are our AC supply, or generally we are obtaining the signal AC supply to our home. Now, what we are doing in the adapter, in the mobile adapter or the charger circuit, now what it is there internally the rectifier circuit is there. Okay, that is what I am telling. Where do we use it? Now, all the practical applications, mobile chargers, laptop chargers, all those things, all the electronic equipments, they will use only the DC power supply. They will not operate at the AC source. If you directly connect the 230 volts AC source to the digital electronics, any gadget, it is not going to tolerate. Now, how to convert AC to DC? Now, 230 volts AC is coming from the outside. Now, we are converting the 230 volts to the 12 volts. That with the help of your transformer. The transformer is stepping down from 230 to 12 volts or something, but that is also the AC signal transformer. Now, how to convert AC to DC? Now, with the help of this rectifier circuit. Now, if you use the rectifier, now what it will do, it will convert the AC signal to pulsating DC signal. Now, to convert the pulsating DC to the pure form of your DC. Now, see, our mobile phone, for example, if the pure form of 5 volts DC is not coming continuously, now this device is going to damage. Now, we need a constant DC power supply to the digital gadget, electronic gadgets. Now, this constant DC, we are obtaining. Rectifier is directly we are not getting the constant pure DC. Output of this impure DC you are giving to DC. Now I will clearly explain you the same thing. Now at the end of this class we are having one more section is there, that is with the filter. Now what is advantage of filter you are asking? Now I will take the capacitor filter, inductor filter, LC section filter. Now with the help of filter, now how you people are able to get the purest form of DC, I will explain you at the end of the class. The main purpose of filter is the filter will convert the pulsating DC into the pure DC. In the pure DC, there is no spikes. It is a constant DC signal. Okay, that is one topic is there for us. The topic is with filter is also there. Now I will explain you what is the filter diagram. Now how the filter is converting. We are obtaining the pure DC at the output of filter that we are going to see at the end of the class. Right. Now we'll see the mathematical part here. Okay, very easy mathematical parts. That is what is the average current, what is a DC current, what is a form factor, what is a peak factor, what is a transformer utilization ratio. Now all those things we are going to see now. Yeah, pulsating DC is getting converted to pure DC by filter only. There are different filter circuits are there. Inductor filters, capacitor filters, now LC, inductor capacitor filters, now tank filters. I think in the BW you people have studied about these different types of filters also. Okay, even though no problem, but in our topic it is there. Now it is a rectifier with the filter, without filter is there. Now with the filter at that time I will explain in detail about the filters, importance of filter. Now how that is, how it is producing the purest form of DC also I will explain in detail. Right, now we will move on to the today's topic. We'll continue the today's one. Shall I continue the today's class? Absolutely. Every device must have, wherever the rectifier is there, rectifier always will follow the filter. If there is no filter means there is no purest form of DC. Okay, right. Now we'll move on to the continuation of the today's class. We can use AC current also. No, where you can use AC current for now. Okay, you people may think that's directly 230 volts. I'm connecting my charger, laptop charger. I'm using the 230 volts. Now see the laptop adapter is there now. That is output of the laptop. Now you see with the multimeter, check with multimeter, output you will get only 12 volts. Now, even though you are not connecting charging to the power supply, the 230 volts, it is operating with the battery voltage. Now every laptop is having the battery. Now what is the battery is the DC current, that is not AC. Okay, right. Now I will take all those things at the end of the today's class because we will complete the today's session. Then we will get the clarity. Right. And now this half-wave rectifier, this is the input signal. I hope you people are having the mathematical representations, integrations and differentiations. You people are very clear. Now the input signal is the Vi. I'm representing this is a sine wave I'm applying now. How to represent a sine wave? Input signal Vi is equal to, it has the Vm into sine omega t. Now this is my input signal, AC signal you are applying to the half wave rectifier. Now we will calculate the parameters. Now we are going to do the analysis part for half wave rectifier. See, today I will explain half wave rectifier, all these 10 parameters. Full wave rectifier is exercise to you people, because nothing is there. What are the derivations we are doing for the half wave rectifier? That is for half cycle only we are doing. A full wave rectifier, that will doubles. Just we are adding the one more half you are adding, that is a full wave rectifier. Now that's why, now follow the today's class clearly. Then full wave rectifier is also exactly same like the half wave rectifier. Formula is same and everything is going to be the same. But what you are going to include in full wave rectifier? There you are going to include the full wave, but here we are including the half wave only. Okay. Now what are the parameters we are analyzing today? What is the DC output current? What is the DC output voltage? RMS current, RMS voltage, efficiency, peak inverse voltage, ripple factor, regulation, transformer utilization factor, and one more the peak factor and the form factor. Okay. Now we are going to see these 10 parameters, how to derive these 10 parameters. And today MCQs, it is going to be a little bit confusion to you people, because we prepared the MCQs only based on the half wave rectifier. Mostly I'm expecting to cover only half wave rectifier, these 10 analysis part. Try to remember the expressions or final expressions. Now those we are going to see in the MCQs part, today's part. Right. Directly I'm moving on to this. Now what is the sinusoidal signal we are applying to the input of rectifier? Your Vi is equal to, now that's why I told you, take a pen and paper. Now parallelly you write all those things. Whenever you are seeing the presentation, what are the expression you are getting, parallelly you solve, then it is you are practicing parallelly along with me. That is very easy to you people to understand also. Input you are applying Vi is equal to Vm sin omega t. Now what is Vm stands for? Maximum value of sine signal. Okay. Now we'll see what is I current flowing through the diode. It is representing, see, voltage signal, input signal, current signal is the sine wave only. Now I current signal you are representing with Im sin omega t. Now where this Im sin omega t, it is 0 to pi. It is what is the current signal you are getting, the output signal? Now output current is flowing only half of the cycle. Here 1, I am taking 0 and the pi, and this is your 2 pi. Now during pi to 2 pi, what is the signal, output signal is 0. Now once again it is 2 pi to 3 pi. Now that's why your current signal, output signal is defined as I is equal to Im sin omega t from 0 to pi. 0 to pi it is a sine signal, and the pi to 2 pi you are defining it is your 0, because output current signal is 0. Right? Now where, what is your Im? Im is the maximum current. This is nothing but your Im. What is I is equal to? Generally from Ohm's law, I is equal to V by R. Now V by R. Now what is your V? V is nothing but maximum value. We are talking about the maximum current. That's what is the maximum voltage by R. What is the resistance R? Now see, here the two types of resistance is there. Diode is having the forward resistance. In the forward bias, it is offering some forward resistance. Now that is, I'm calling as, this is your RF. Very small resistance is there. It is in series with your RL. Now that's why whenever you are considering the resistance, that is RF plus RL. Now see here. Now what is your maximum current Im expression? V by R. Now Vm by Rf plus RL. Now take, this is one more expression. Now input signal Vi is equal to Vm sin omega t. The current signal is defined as I is equal to Im sin omega t during 0 to pi, and it is 0 during pi to 2 pi, because it is rectifying half signal only, remaining half is 0. Now first we will find out what is average or DC output current. Now what is I average value we will find out. What is the average current expression? The average DC current is given by 1 by 2 pi into square root of I dt. This is I dt is nothing but, this is a expression for your DC current or the average current. Okay. Now this is 1 by 2 pi into 0 to 2 pi. The complete cycle, it is having the average value. But what is the output? It is, I'm dividing into 0 to pi and pi to 2 pi. Now this is, here it is not there. It is from 0 to pi. Now what is the current value? Im sin omega t into d omega t. From pi to 2 pi, what is the I value? 0. Now that's why this expression is going to be cancelled, the 0 value. Now you take 1 by 2 pi, Im, take the Im is a constant factor, take the Im to the outside, and sine omega t is nothing but your minus cos omega t from 0 to pi. Now substitute the values pi and 0. Now it is becoming Im into minus 1 half, take the minus is common. This you are getting, what is the IDC value? Im by pi. Remember, this is very, very important. The first expression we are getting, what is average DC current? Average or the DC current IDC is equal to maximum current Im by pi. This is the first expression we derived. Now what is the DC current? Other name of DC output current. This is DC output current or the average output current. These two terminology is same. In the MCQs, I may ask you I average or I may ask you IDC. IDC, I average, both are same. Now what is the expression for IDC? IDC is equal to Im by pi. Now what is the pi value? 3.14. Now if you are dividing 1 by 3.14, that is equal to 0.318 into Im. But remember this only, this is the standard expression you are having. Now from this expression, what is your Im value? Your Im is already, what is your Im is equal to Vm by Rf plus RL. Now substitute this value here so that this Vm by Rf plus RL is nothing but your, this is your Im by pi. Is it clear? Now another way of representing the DC current is, the first value DC current is see, the first expression is nothing but your, what is the DC current? IDC is equal to, your IDC is equal to Im by pi. It is representing in terms of max currents, maximum current. No, if I want to represent in terms of voltage, now what is the other form of representation? That is Vm by, this pi is there now, pi into Rf plus RL. Now this is the DC current of your rectifier. Now can you tell what is the DC output current of your full wave rectifier? For half cycle it is 1 Im by pi. For the full cycle it may be 2 Im by pi. That is, for the full wave rectifier, your IDC is equal to, that is 2 into Im by pi. That means the two parts it is going to be rectified. Double of half wave rectifier is full wave rectifier. Now there the signal is available from the pi to 2 pi is also current signal is there. So that you are getting 2 Im by pi. That we will discuss in the full wave rectifier case. I hope DC current is clear. What is the DC current? It is how to represent the IDC. This is an expression for us. IDC is equal to, for the complete cycle, 1 by 2 pi into integral of 0 to 2 pi I dt. This is the expression of your DC current. Now substitute the current expression I value. From 0 to pi it is, current is flowing. Pi to 2 pi there is no current flow. If you are solving, you are getting Im by pi, as well as in terms of Vm, if you are writing Vm by pi into Rf plus Rf. Now this is the first expression we have seen today. Right. Now what is the average or the DC voltage? Now we derived the DC current. What is the DC current? IDC is equal to Im by pi. This is in the previous expression. Now what is the average voltage or DC voltage? Now what is V is equal to I into R now? V is equal to I into R. Now if VDC, you want the VDC value, now that's why I is also DC into here R is nothing but the load resistance, where you are obtaining the output voltage at the load resistance. That's why now already you know what is IDC is equal to Im by pi into RL. Now this you can represent in terms of what is Im by pi. Now Vm by pi into RL plus Rf into RL. Now that's why from this you can write VDC is equal to Vm into RL by pi into RL plus Rf. Now this is the DC voltage expression. It is clear, I hope. Now, for example, if the load resistance is, we are choosing, generally load resistance is very, very high compared to forward resistance. In the forward bias, it offers very low resistance value. Now, if you neglect this, now what is VDC is equal to Vm by pi. Now, from this we are concluding the DC current IDC is equal to Im by pi. And what is your DC voltage? VDC is equal to Vm by pi. Now, this is expression for DC current as well as the DC voltage. Is it clear? First expression is clear. Is the first part is clear? Shall I move to the RMS current? Yes. Okay, right. Now it is better to take the pen and paper. If you take the pen and paper, it is very easy. It is not that much complicated. All are very, very small, easy derivations for us. Right. Now we'll see RMS current. What is RMS value? Root mean square value. Now IRMS is given by, this is root mean square, half is square root of. This you are going to see, I'm representing 1 by 2. 1 by 2 pi into 0 to 2 pi. I square into d omega t whole power 1 by 2. That is generally you are writing RMS. Square root of you are going to write. Instead of square root, I am writing the 1 by 2. Whole power 1 by 2. Okay. Now, what is RMS value? RMS is equal to 1 by 2 pi into 0 to 2 pi I square into d omega t whole power 1 by 2. Now, once again you split into 0 to 2 pi. Now current is available, output current is available during half cycle only. Now that's why, now during the positive half, 0 to pi, the current, what is I value? I into sine omega t. I square is nothing but Im square into sine square omega t into d omega t. And during the pi to 2 pi, what is the current value? I is equal to 0. Now that's why this portion is becoming your 0. 0 into something is 0. Okay. Now how to represent sine square omega t? Already people are know all the integrations part. Sine square is 1 minus cos 2 omega t by 2 into d omega t. Now take the Im square as common, Im square by 2 pi here. Okay. Then Im square by 4 pi. Now take this 2. Now here 2 is there now. Take this 2 also to the outside common. It is becoming Im square by 4 pi into omega t minus half sine 2 omega t whole power 0 to pi whole power 1 by 2. Now if you are solving this, now you are getting simply finally Im by 2 your RMS value. IRMS you are getting. Now just go through this. Now IRMS value is equal to Im by 2. Now what is IDC value? Previous expression. IDC is equal to Im by pi. IDC is Im by pi and IRMS is equal to Im by 2. Now this is the expression for your RMS value. Just to go through this, everything is I gave you clearly. This I solved it clearly with respect to this all those values. Now from this conclusion, what is IRMS value? IRMS is RMS current is given by Im by 2. Now therefore, another way you can represent what is Im value, Imax value. It is Vm by Rf plus Rl. Now this may represent in terms of Vm. The IRMS is given by Vm by 2 into Rf plus Rl. This is the RMS value. Now what is the RMS value? RMS current. IRMS is given by Im by 2. Im by 2 is the RMS value. Im by pi is the DC value. Now if you are representing in terms of the voltage, now what is this given by? Im is replaced by Vm by Rf plus Rl. That's why Vm by 2 into Rf plus Rl. Now this is IRMS value. So third one we have. The next, what is the output RMS voltage? Now this is the RMS current. Now like the previously we calculated output voltage now, because IDC, see here, IDC, after calculating IDC Im by pi, we calculated the output voltage also, DC voltage. What is V is equal to IDC into RL. Now here also we calculated IRMS value, RMS current first, then we'll go for the RMS voltage. Now what is, how to calculate RMS voltage? The RMS voltage is given by the same thing. Now V is equal to I into R. Now what is VRMS is equal to IRMS into RL. This is a simple expression. See, like the same thing. Here it is a DC value. That's why I is DC multiplied by RL. Now if you are calculating for RMS voltage, now this current is RMS current multiplied by RL. Now what is IRMS value? Here IRMS is equal to Vm by 2 into Rf plus RL multiplied by your RL. V is equal to I into R now. I is nothing but this is your IRMS value multiplied by RL value. Same, just same like the just take the consideration. Always load resistance is very very high compared to forward resistance. Now in this case, now you can neglect your RF value. Now what is becoming RL is going to be cancelled. Now your VRMS is given by VM by 2 straight away. Okay, now these four expressions I am writing once again here. Now what are those four expressions here? Now first one is, what is your IDC current? The DC current or average current is given by IM by pi. Now what is your DC voltage? Now VDC voltage is given by VM by pi. That's it. VM by pi. After considering RL is far greater than RFL. Now third expression is, what is RMS current? IRMS is given by IM by 2. This is IRMS value. Now what is your RMS voltage? Now VRMS is equal to VM by 2. These are the four expressions. Remember these four expressions till now. Okay, I hope these four expressions are clear to everyone. Because see, this is nothing but your I into R, you can write. So V is given by I square into R. Now that's why DC power is given by I square into R. Here it is a DC power. That's why current is also DC current we are going to consider. Now that's why I square DC into RL. Now what is IDC value? Your IDC is nothing but your IM by pi. Is it clear? IM by pi. Now what is I square value? IM square by pi square. Pi square. Now that's why IM square into RL by pi square. This is a DC power. The next one is the AC power is given by I square into RL. And now that is I square RMS into RL plus RF. We are considering, we can remove this also. IM square by RL plus RF. This is IRM square into RL is power dissipated. This is across the load. This is nothing but across the diode. Now, in this case, we are going to consider the two things. Across the load we are considering, across the diode we are considering, because two resistors are there. Now here we are giving by eta is PDC by PAC. Now from this DC power is, this is a DC power multiplied by AC is nothing but reverse this. The 4 by IM square into RL plus RF. And now if you are solving this, you are getting take the 4 by pi square is outside. The 4 by pi square now into RL by RL plus RF is the value. Now so that you are getting, if you pi is 3.14 now, you can take 0.406 into RL by RL plus RF. Okay, it's the same thing. You can take this RL as a common here. This RL you take to the denominator part, RL by RL and RF by RL. It is 4 by pi square into 1 by 1 plus RF by RL. From this, you can define the efficiency is equal to 40.6. The by 40.6 in terms of your percentage. If you are multiplying with the 100, what you are getting the 40.6. The by 1 plus RF by RL. Now generally RL is very large compared to RF. so that this factor is very small. Okay, now efficiency is becoming 40.6. Now that means, now what is happening? The half wave rectifier efficiency is very, very small. Already we discussed. Now, maximum power cannot be transferred in half wave rectifier. The efficiency is also very, very poor. Only 40% of efficiency is there for the half wave rectifier. Now that's why in the practical applications, we are not going to use this half wave rectifier. Is it clear? Now, theoretically, maximum value of rectifier efficiency of half wave rectifier is 40.6 when RF by RL is equal to 0. When RF by RL is becoming 0, if the forward resistance is 0 by something, it is becoming 0, then 40.6 by 1 is nothing but 40.6. Now, final concluding, what is efficiency of half wave rectifier? The efficiency of half wave rectifier is 40.6 only. 40.6 means even 50% efficiency is also not there for half wave rectifier. Now that's why we are not going to use this half wave rectifier for the practical applications. We will use the full wave rectifiers. Next factor is ripple factor. Now what is the ripple factor? The ripple factor is how much ripple is there. Ripples are present in the signal, that is given by ripple factor. Now ripple factor is given by, this gamma is given by square root of IRMS by IDC whole square minus 1. Okay, or in terms of voltage, if you want to write this, gamma is equal, that means it is equal to VRMS by VDC whole square minus 1. See, you people have to remember the first things. If you remember the basic formula for the first one, then these values you can easily substitute. You know IRMS value, IDC value, VRMS value, VDC value, you know. Now, you must remember what is the basic expression for the ripple factor, form factor, peak factor. If you remember this expression, then you can easily substitute the values. What is IRMS value? Im by 2. What is IDC value? Im by pi whole square minus 1. Now, if you are rearranging this, you are getting pi by 2 whole square minus 1. Im is going to be cancelled. Pi by 2 whole square minus 1. Now, if you are solving this, you are getting ripple factor R is equal to 1.21. Now, what is this figure is? The ripple factor will tells to us how many ripples will present in the output signal. Now, if the ripple factor is equal to 0, that indicates there is no ripples in the output signal. That is purest form of your DC. Ultimately, we are expecting the less ripples. If we are having the ripple factor is very low, then with the help of the normal filters also we can remove. But even though it is ripple factor is more also, now we are going to use a filter at the output side. The filter is compulsorily we are going to use. But this factor will tells to us how much ripples percentage is there. That is given by the ripple factor. What is the basic expression for ripple factor? That is IRMS by IDC whole square minus 1. Okay. Now, or you may write VRMS by VDC whole square minus 1. Now, this is the expression for your ripple factor. Right. The next one is the peak inverse voltage. What is a peak inverse voltage? The name itself it is given. It is a peak inverse voltage. Now it is defined as the maximum reverse voltage that a diode can withstand without destroying the junction. Now already I discussed on the breakdown mechanism. What is the breakdown mechanism? If you are applying the reverse voltage, now if you are applying the more and more reverse voltage, at some point of time a breakdown will occur. Breakdown in the sense a sudden change in current, suddenly huge amount of current is flowing to the diode that causes the breakdown to occur, that will result the damage of the device. Now, what is this value? The peak inverse voltage is nothing but it is defined as the maximum reverse voltage that a diode can withstand without destroying the junction. And before breakdown occurs, now what is the voltage? Up to what voltage? Now it can tolerate. That is given by the peak inverse voltage. Okay, inverse is the reverse voltage. That's why without destroying the junction, up to what extent it can withstand, that is given by the peak inverse voltage. Now peak inverse voltage is given by the peak value of peak of the negative half cycle. Now what is the peak negative half cycle peak? Now if you take this is a peak of the negative half cycle, positive half cycle. Now this is the signal. Now what is this value? This is a VM, positive VM. And what is this is nothing but your this is also VM. Now what is, now we are discussing about the reverse voltage only. This is a reverse case during the negative peak. In the negative peak, what is the maximum peak value here? The maximum peak value is nothing but your Vm. Vm is the maximum peak value. Now that's why, now what is the peak inverse voltage? The peak inverse voltage of half wave rectifier is Vm only. Why it is Vm? During the negative cycle, the maximum, see, if you consider the complete cycle, the value is the positive plus Vm is 2 Vm it is. But how to calculate the peak inverse voltage? Peak inverse voltage will be for only negative half cycle. For the negative half cycle, what is the maximum value you are having? Vm is the maximum value. Now that's why PIV value is given by the Vm. There is no expression for this. Only the definition is there for peak inverse voltage. The peak inverse voltage of half wave rectifier is Vm value. Now once again I will write all the things whatever I discussed till now. Now what is our DC current? IDC current is given by Im by pi. Now second one is IRMS is given by Im by 2, or the VRMS is given by Vm by 2, or VDC is given by Vd by 2. Now next fourth one is we came for your this is efficiency. What is efficiency of half wave rectifier? The 40.6 only. This is efficiency of half wave rectifier. Now what is the ripple factor of half wave rectifier? R is equal to 1.21. There is a ripple factor of half wave rectifier. Now what is the PIV value of half wave rectifier? Peak inverse voltage of half wave rectifier is Vm only. That is the peak inverse voltage of half wave rectifier. So these are the things we discussed till now. And next two more parameters are there. Now that is next one is given by this is regulation. Now here it is not visible to you. The regulation, percentage of regulation, how much it is regulating. Now the variation of DC output voltage as a function of DC load current is called as a regulation, percentage of regulation. How much it is regulated, that is given by the regulation factor. Now the variation of VDC with IDC for half wave rectifier is given by, now how to obtain for half wave rectifier, regulation for half wave rectifier. Now already you know what is IDC value, just we are recalling, IDC is equal to Im by pi. What is Im by pi? Im in terms of, you can write Vm by pi into Rf plus RL. See, this you are writing in this way previously, Vm by pi into Rf plus RL. This is expression of IDC. But here how to represent this? In this way also you can represent Vm by pi. I am taking the pi to the numerator part. Denominator is Rf plus RL. Okay. And now, but what is our VDC? See, I am not came for the final one. What is the VDC value? VDC is given by IDC into RL. Okay. Now, what is IDC value? Now, you take this as a value. The IDC value is given by the Vm by pi. Actually, Vm by pi into Rf plus RL. This is the IDC value. Now, see, this is IDC value multiplied by RL. This RL is comes to here. Okay. Now, that is given by Vm by pi into, now you take the RL by RL, you can take, that is a 1 minus Rf by Rf plus RL. So that's this Vm by pi, multiply the same value minus IDC into RF. So that the VDC value is given by the Vm by pi minus IDC into RF. Okay, this is the variation of VDC, the variation of this VDC, output DC voltage. Now with respect to IDC, now this is IDC is given by the regulation value. Now just you obtain the value of VDC in terms of IDC. So regulation is generally till now I am not seen this regulation in the examination papers also, but try to remember the definition. What is the percentage of regulation? The variation of VDC or the output DC voltage as a function of output DC load current. This is the expression for your regulation value. The next one is the last one. I think this is the last one is transformer utilization factor. Now, what is the utilization factor? Transformer utilization factor. It is defined as the DC power to be delivered to the load in a rectifier circuit that decides the rating of the transformer. That means, what is the rating of the transformer? Now that is given by, that is decided by the DC power which is delivered to the load. Now if you take a load resistance here, now how much DC power that is delivering to the load, now that will decides the rating of the transformer, sorry, not the transistor. Now the transformer utilization factor is defined as, TUFL is defined as, remember this, the TUF is defined as DC power to be delivered to the load, how much DC power is delivering to the load, divided by AC rating of the transformer, secondary transformer winding. Now what is the rating of the transformer of secondary winding? Now in simple, the TUF is defined as PDC. PDC is nothing but this is the power delivered to the load, DC power delivered to the load by the AC, rated the AC rating of the transformer. PDC by PAC rated. Okay, this is the expression for your transformer utilization factor. Now the factor which indicates how much it is utilization of the transformer in the circuit is called the transformer utilization factor. Now already the name it is saying how much you are using the transformer, how well you are using the transformer in the circuit, that is given by the transformer utilization factor. 100% you are utilizing the transformer means the TUF will be the 100%. Only 30% you are using, that is given by the TUF factor. Now what is the TUF, this factor? Now this TUF factor, it indicates how much is the utilization of the transformer in the circuit, which is called as a transformer utilization circuit. Okay. Now the AC power rating of the transformer is given by, what is expression for AC rating of the transformer? That is, the power is generally V into I, VRMS into IRMS, because it is a AC power now. For AC, AC voltage multiplied by AC current. Okay, this voltage is nothing but the rated voltage of transformer, secondary transformer. Now the secondary voltage is purely sinusoidal signal, hence its RMS value is 1 by root 2 times the maximum, while the current is half sinusoidal signal. Now the RMS value is half of the maximum value. The RMS value is nothing. What is RMS value? Vm by 2, half of the maximum value. Now you are taking IRMS is equal to Im by 2 now. What is Im by 2 in the sense? Half of the maximum value. VRMS is nothing but your half of your maximum voltage. That is a simple value. Finally, transformer utilization factor is, it is the utilization of transformer in the circuit. It indicates the utilization of transformer in the circuit. It is defined as the DC power delivered to the load by the AC rating of the transformer secondary winding. That is given by transformer utilization factor. And now a simple thing, see this. Now what is the AC rated value? Now the AC rated is given by the PAC. The secondary transformer rated is, here we are already having VRMS into IRMS now. This is expression for PAC. What is VRMS value? That is Vm by root 2 into Im by 2. Now this is expression for this. Okay, that is Vm into Im by 2 root 2. Now the DC power delivered to the load is I square DC into RL. Now this IDC is nothing but Im by pi whole square into RL. So therefore the TUF is given by PDC by PAC rated. Now the PDC is given by, this is a PDC value and this is a PAC rated value. Now if you are calculating this with the approximation, Vm is approximately equal to Im into RL. Now the TUF factor will be 0.287. This is the transformer utilization factor of your half wave rectifier. Now the value of TUF is low, which shows that in half wave rectifier circuit, the transformer is not fully utilized. If it is in the percentage fashion, how much percent it is utilizing? Only 28% only transformer is using. That means remaining 72% transformer you are not using. The wasting the power of the transformer. So that's why half wave rectifier only 28%. That means TUF factor is 0.287. Now we are not fully using the transformer. Only 28% of the transformer we are using. That's why half wave rectifier we are not going to use in the practical applications. Okay, this is the transformer utilization factor, TUF. The value of TUF is 0.287. If you want to represent in terms of percentages, it is 28%, 28.7% only. It is utilizing the transformer. Okay. Now the last factor is there. Only the small, that is, I think this is a peak factor. I think only 3 minutes time is there for us. the form factor and peak factor. Now, what is a form factor? The form factor is defined as RMS value to average value. Now, for all these 10 expressions, you remember the first basic formula. If it is clear to you, then you will get everything easily. Now, what is a form factor? It is RMS value to average value. Average value, other name of average value is the DC value. RMS value is Im by 2. Now, average value is nothing but Im by pi. Now, from this, if you are calculating this, you are getting 1.57 is a form factor. Form factor is given by, it is defined as RMS value to average value. Now, form factor is 1.57. Now, what is a peak factor? The peak factor is defined as peak value to the RMS value. What is a peak value? Now, for this output waveform at the output of the rectifier, what is this peak value? This peak value is Vm only. That's a peak value is Vm. RMS value is Vm by 2. So Vm will be cancelled. The peak factor is 2. Now this is the value of peak factor. Now how to define the peak factor? Peak factor is defined as the peak value to the RMS value. Now these are the analysis part of your half wave rectifier. Now what we are discussed for the half wave rectifier, just I'm summarizing the briefly. Now first, from where we started at the DC current or the average current. Now what is the DC current is given by? DC current is given by maximum current Im by pi. Now this is nothing but DC current, or DC voltage is given by VDC is equal to Vm by pi. That is the first DC values. Next we discussed about the RMS current. IRMS is given by maximum value Im by 2, or VRMS is given by Vm by 2. This is the DC voltage and the DC current, and the AC voltage and the AC current. Next we calculated the efficiency of the transformer. Now what is the efficiency of your half wave rectifier? The efficiency of half wave rectifier is 40.6 only. Only 40% efficiency only we are getting with the transformer, this half wave rectifier. Now after discussing efficiency, then we came up with the regulation value. What is the regulation factor? The variation of output DC voltage, the DC voltage with respect to the output DC current, that is given by the regulation value. That is a value is given by that value. Then next we discussed about the transformer utilization factor. What is the transformer utilization factor? That is a DC power delivered to the PDC, DC power delivered to the load by PAC rated value. What is the PAC rated value? That is the transformer secondary winding. What is the rating of the secondary winding? That is a PAC rating value. What is the TUF value? Transformer utilization factor is 0.287 only. That is only 28.7% we are using. That is the transformer utilization factor. Then next we came with the form factor. What is the form factor is given by RMS value to average value. Now what is the form factor of half wave rectifier? Form factor is equal to 1.57. And next we came with the peak factor. The P is given by the 2. Now these are the analytical part of your half wave rectifier. The same parameters we are going to calculate for the full wave rectifier in the next class. Okay. Now I think full wave rectifier, you people has to derive all those things. You have to tell. Now what are all the 10 parameters? Now from starting from the IDC to the peak factor. Right. Everything I covered, I think. Okay, one more, peak inverse voltage and ripple factor I have not covered. The ripple factor is given by the square root of RMS current to the DC current whole square minus 1. Ripple factor is given by 1.21. 1.21 for the half wave rectifier, and the peak inverse voltage of half wave rectifier is a Vm. These are the two things at the time of summary I am not covered. Right. Now with this I am stopping the today's class, and now full wave rectifier will start in the next class. Okay. Now